Now, suppose that I go back and I vary the biasing voltage from 1.5 volts to 1 volt. The impedance looking in the transformer still is the same because it's not really affected by the biasing of the transistor. But you can see what happened here. The center frequency stayed the same, but the gain changed. It's about half as big, and likewise here too, from what it was in our previous case. And the reason is that we've changed the gain of the circuit. So if we lower the value of voltage fed back, we'll actually lower the gain. And that's what's happening in the automatic gain control circuit. Things got louder, that DC level was going down. The value of Q here went up a little bit, and the reason, most likely, the fact that RO, transistor rate, actually increased from about 90K to 227K. The effect of the automatic gain control circuit, changing the biasing of the first IF amplifier, will cause its gain to change, still be the same center frequency, change Q a little bit, but not by a lot, but lower the gain, so that we could then have a fairly constant signal in the audio amplifier stage. And you'll play with this in lab as you build the AM radio section. The last section of our AM radio deals with the AM mixer and AM oscillator. If you look back at the block diagram on page 2, but also included with this stage is another RF amplifier. This is seen on page 21. Let me make this a little bit smaller so that we can see the whole schematic on the screen. And again, there's quite a few things going on here. Just trying to get a qualitative understanding of what's going on. We're going to use SPICE to help us figure those things out, but of course in lab you get a chance to take some of the measurements. Start over here on the left-hand side. This capacitor C28 is 0.1 microfarad, so at RF frequencies, around 455 kilohertz or so, this is going to look like a short circuit. And so that's going to connect this point to node 1, which is the battery, and that'll short back to ground. So this variable capacitor is in parallel with the primary side of this particular transformer to form a resonant circuit. So it's going to let only one signal pass, and that's going to be our received radio station. And then that signal will show up here through this transformer. Here too, this is a fairly large capacitor, so that at RF frequencies this would be a short circuit. So that voltage then is hooked up to the base of this transistor, which forms a one-stage amplifier. So with this being a short circuit, we also have this variable capacitor in series with this fixed capacitor. Now form a product over a sum from here back to ground. Now I've got an L4 and an L5 from T5's transformer, and this capacitor too, being fairly large, would be a short at RF frequencies. And so if that's shorted to here, what I've got is a resistor in parallel with L5. This is sort of the structure of our tapped L circuit that we had back in chapter 1 on page 89 of the lecture notes. So the equivalent capacitance seen here sees two inductors, which are effectively in series, and then the transform resistance in parallel with all of that. And that too is going to form a resonant circuit, letting only one frequency through. What we'll see in a little bit is that this actually forms an LC oscillator, and the frequency that's going to come through is just that of the resonant circuit frequency. We're going to calculate that in just a minute too, and then we can compare that in the simulation. The transformer up here, T6, is pretty much being used as in the previous amplifier, IF amplifier cases, where we've got the input going to another stage, and it's giving us some effective resistance between the two pins of the secondary side of the transformer. So what this is going to do is it's going to be tuned for 455 kilohertz again, and it's going to give us a bandpass filter, so whatever is present here, only one frequency will be allowed to come through, and that's going to be the 455 kilohertz signal. Now we could calculate the biasing point of the amplifier, get some idea where some of these numbers are going to be sitting at. And so let's go back and zoom full screen again here. And so if you neglect the base current coming in here, you have a voltage divider with 12K and 56K with a 9-volt battery, and that would give you a node voltage here of about 1.588 volts. If there's a 0.7 drop across this PN junction, then this node voltage would be about 0.888 volts. And then we could calculate the emitter current, because this is a capacitor, and so no average current will pass through here, and so the current in here then would be the 0.88 volts divided by 3.3K, and that gives us about 270 microamps of emitter current, which would then be roughly the same as the collector current. So the transistor could be biased through this being a short circuit for DC, a short circuit for DC, and then back to 9 volts here. So there's a path for current to flow to bias the transistor. On the following page are some of these calculations. Let's take a look at that on page 22. Here are the DC calculations. And as we said previously, the variable capacitors with the coil in transformer 7 will form a resonant circuit, and this will be the frequency that we'll be receiving. And then the other resonant circuit, which will actually become part of our oscillator, has got a series combination of a variable capacitor with a fixed, and then this tapped L equivalent circuit, if we ignore the coupling effects with the other side of the transformer, just again for approximation, would be the sum of the two inductors plus their mutual inductance times 2. So that would, again, like our tapped inductor circuit. So I'm going to use those calculations to see how close that comes to some of the simulated results, and then of course you can see the similar things in the actual circuit as you measure it. And then this last part here with transformer T6 is giving us a bandpass filter, just like our other IF amplifiers, and this is going to be tuned to 455 kilohertz. What's on page 23 is a simulation of this oscillator, RF amplifier, and mixer. What I'm going to do is take the received signal transformer and replace it by just a voltage source, really 3 voltage sources that are going to mimic the equations of a modulated signal. And I'm going to set the frequency at 624 kilohertz as the received signal, an audio signal of 1 kilohertz. I'm going to set the carrier voltage to be very small so that we can watch what happens before we receive the signal. We're going to bump this up in a few pages and watch what happens as it passes through the circuit. The transformer T6 is, again, like our IF transformer, where with perfect coupling we would have a mutual inductance effect. And so I've picked the values here such that there is a bandpass filter at 455 kilohertz. And these were arrived at by measuring roughly what the coil's inductances were, and I varied the capacitor a little bit so that I could get the filtering frequency to be 455 kilohertz. And of course, in lab, you'd be tuning the coil a little bit with this capacitor fixed, but its value is very close to this. Then transformer 5 is part of the oscillator circuit, and again, I'll use perfect coupling, and so I've got a mutual inductance effect to also take into account. And this is going to oscillate actually at this resonant frequency of about 1.08 megahertz with the values of the C and the L's that I had. A couple other things also in the simulation. When I ran it initially, I found that one of the transformers actually ran off to infinity because my model is just simply an inductor. We've got a feedback loop from the output back to the input. We're going to look at that in just a few pages or so. When I'm putting back-to-back Zehners across the terminals of 46 and 47, and with this equivalent set of numbers, about 6 volt Zehners. So if the current flows this way, you'll get 6.7. If the current flows this way, you'll get minus 6.7. In the real transformer, you'll get magnetic saturation, which would limit the voltages from running away, but our modeling is much simpler than that. So I had to add this because in lab I measured the voltage across that transformer and it never exceeded this value. So I stuck that in as a kind of a limiting factor. We can see on the next page is some of the waveforms that were found in the simulation. The first one here is the voltage across nodes 46 and 47, and this is the coil L4. You can see that there's a perfect sine wave here with a frequency of about 1.08 megahertz. This is going to be my oscillator frequency. Likewise, from node 0 to 46, I'm finding the voltage across the coil relative to the dot notation on page 21. Here too you see a sine wave. And then at the output of the transformer across the coil L6, I've got a sine wave. Now they're all in the same phase because I'm looking at the voltage from plus to minus where the plus is on the dot. Also note here that the average value is 0 because the voltage across an inductor for DC is 0. So in steady state we'll have these 0 volts across each of these. What's kind of interesting is that although these voltages across the coils are all sinusoids, when you actually look at the currents, it's quite a different story. So in lab all we can do is measure these voltages, which appear to be nice clean sine waves, but in reality the currents are being switched on and off. Take a look at that in just a little bit. This is the voltage across the resistor R33. This is our biasing resistor, and we were estimating that the biasing voltage, which would be the average value here, is around 0.88 volts, so it's somewhere around there. Now I'd like to show you how the oscillator is working again qualitatively, and I thought I would do this with 4 time instances. I've marked them here as T0, T1, and T2. Let me zoom on this just a little bit here. This is the current on the primary side of transformer T5, which I called coil L4. Take a look at some results here in steady state. Taking a look at some of the values of the current and watching what's happening in the loop and kind of show you how the oscillations are sustaining themselves. So I'm going to go back to page 21 shortly and refer to the time T0, T1, T2, and T3. And I'll use the same colors as I talk about the results on the transformer. And then you could just take a ruler and just connect these points up and you kind of see what's happening. So here I'm on this slope of L4 current, and then the transformer winding just below it is L5. And those same points are marked here. This is the current in coil L6, which is also hooked up to the collector of transistor Q7, so it becomes its collector current. You can see here that the current actually goes to 0, so the transistor is being turned on, turned off, turned on, turned off. The frequency of this signal is 1.08 megahertz. So it has an average value and then has peak values here with no signal coming in, and we'll see when the signal comes in that these peaks begin to vary. This is the current that's in the resistor R33. Looked at the voltage across it, and of course just dividing by R you get that. And these same 4 points are marked on here. And then this is the current in the capacitor C31. And again, these same 4 points are marked here. Let me go back to full size again. Let me go back to page 21, and you can keep an eye on this page while I'm doing that.